All right. Okay. We will start the second textbook, ocean engineering. So, first topic is coastal properties. The young will lecture first, and then myself, and then there will be a discussion by Bonjin. The question, the midterm exam was graded by TA and then handed over to me. So I'm doing a second review. I probably finish up by this weekend, hopefully. And then next week we can get the result. Any other questions? No, then we can start. That's right. Yes.
I start the lecture. Hi, this is Jeong Jo. Today, I'm going to talk about coastal processes and ocean observations. And this is the new book. This is the chapter for the new elements of ocean engineering. Today, I'm going to talk about chapter 4. Chapter 4 contains like this. And the final topic that I took today, the hindcasting, secondary flow, and the command spider, upwelling, recurrent, lower current, slow current, and gyres. First, the hindcasting. Hindcasting is a quite opposite meaning of the forecast. It uses the best data to predict the futures. So it known or closely estimates inputs for past events to enter into model to see how well the output matches the known results. And it is also called as backtesting. And this is the secondary flow. So secondary flow is when you imagine the cylindrical containers and when you stir the water inside the cylindrical container. Firstly, you can see the concentric flow around the cups, and then the bottom side, the fluid flow to the radial directions, and that's centric flow and radial direction flow are combined, and you can see finally the vortex inside the cup. that is the secondary flow. So this is the examples of secondary flow. Let's watch the videos.
Again, the pattern seems to be one of nearly circular flow. The water going out of the drain must come from the bottom. Holds the tip of the needle about 1/8 of an inch off the bottom. We can see that the dye goes rapidly toward the center, and this seems to be the answer to our question. Primary flow. Here, this departure from the general situation is called secondary flow. Let's see if we can get the tea leaves are a little denser than the liquid, and an experimental model of this flow in order to examine flow going. The tea leaves are a little denser than the liquid and settle slowly toward the bottom. Since they are denser, we might expect centrifugal force to throw them outward and to find them around the perimeter of the bottom of the cup.
This is the Ackermann spider. The Ackermann spider is some bind flow of the ocean surface, and because of the earth and wind rotations. So when the depths change to the under the sea, the angle of the current is changing continuously like this. So deflection of surface currents near horizontal boundaries and Ackermann layer depth is about 50 to 100 meters. And this is coastal upwelling and downwelling. Upwelling is the phenomenon that when north wind are blown to the nearby the coast, so the surface water is go to from near the coast to the off sea. So they make some empty space around the coast. So deeper water moves up to replace the surface water. This phenomenon is upwelling, and downwelling is quite opposite phenomenon of the upwelling. So south winds are blowing, and because of the Coriolis effects, water is go inside to the coast. So the water fires up at the coast and moves to the deeper levels. This is the downwelling. And this is other examples of welling. First one is offshore wind. It's quite similar as the wind from the north. So when the sea surface of the water goes out to the deeper sea, then the upwelling is occurred. And next one, this is the développement. When some obstacles in the deep sea, the current flow is go up through the surface of the développement like this. So the upwelling is different. And final one is the last one is when the surface current flows nearby the coastline, and when there is sharp wind in the coastline, in this side the upwelling is occurred like this. And this is Langmuir or Langmuir circulations. So when you observe it, when you observe the ocean, you can see the white, you can see the stripes like this. This is for the Langmuir circulations. This is caused by the wind, steady flow winds. The picture of the Langmuir circulation is slow, shallow, and some counter-strike circulations here, like this. And then the stripes, it's called the streaks, are aligned with the wind directions. This is the Langmuir circulation. And this is the lake current. When you go to the beach, maybe you can see these phenomena like this. So let's see the videos of the lake current.
You might have heard them referred to as undertow or riptides, but these ocean phenomena are actually rip currents. Rip currents are narrow currents in the surf zone that move quickly away from shore. A typical rip current ranges from 50 to 100 feet wide and can extend 100 yards or more offshore. It can reach speeds of over 5 miles per hour. That's faster than an Olympic swimmer. That makes them dangerous and potentially deadly, and scientists want to learn more about them so we can better forecast when and where they will form and keep beachgoers safe. Here's what we know. Waves don't have to be huge for a rip current to form. 2 or 3 feet are all it takes. And the weather doesn't have to be bad for a rip current to emerge. They often occur in the nice days after a storm. They're usually strongest near low tide, but can form at any time. Rip currents often form where sandbars are near the shore. They occur at breaks or channels in the bar. They're often difficult to see, but you can spot them in areas where waves aren't breaking or where there's foam, seaweed, or discolored water being pulled offshore. It's easier to see a rip current from higher up, such as from the beach access over dunes or a lifeguard's tower. Rip currents are a hazard for beachgoers, but by knowing the dangers and what to look for, you can avoid being caught in the grip of the rip.
This video was the wind current. So wind current or wave energy is keeping shoreline. Same as you can see, some streams of the waters returning to the oceans like this. So as the video says, it's very dangerous for swimming. So just be careful swimming here. This is longshore currents. Longshore currents is when the waves come to the coast, and when the wave reaches the coast shorelines, it makes the longshore current. It is parallel to the shoreline like this. So this is the energy strength distribution of the longshore current. This is a daily sea breeze or the I don't know how can I say it, but sea breeze is caused by a pressure difference between the oceans and lands. Due to the heat capacity differences, in the daytime, the lands heated up more rapidly than the oceans. So the heat air go up through the sky, and the cold air goes down to the ocean. So this such a difference makes some pressure difference. So the sea breeze is happening occur. At the night time, the is quite opposite to the daytime. So the land breeze is well, this is the ocean surface current around the world during the period of 2005 to 2007. So let's see the streamlines. This is all the this is the simulations made by the MIT GC, eddy resolving simulation. This is almost same as previous video. And this is just a simulation, so I will skip this. And this is the mesoscale eddy. I will talk about now the mesoscale eddy. The mesoscale eddy tends to hundreds of kilometers in size, and it usually separates from the main streams and makes little pores around the streams. So this is the principle of mesoscale eddy formation. First, the stream around the streamline there is the warm water and pore populations like this, and the times goes by, the warm water is separated from the mainstream, and then the cold ring is separate from the mainstream. So this is called the mesoscale eddy formations. And this is the root current. Root current is occurred from Caribbean Sea and goes through the Gulf of the Mexico and go out to the Atlantic Oceans. That is, so its features is it cause the root current is the hot and warm, not hot, warm waters. So it is strong, it transports, and it affects hurricanes size and strength and path. And this is the speed of the root current. And this is transparent to Southwest scale simulations. This is not so the video is not sorry. Very explain simply. So these shapes of every single streamline flows like this here, and so here's some pores around the main streams. This is, I think this is oceanic surface, oceanic velocity, and it simulates root current and mesoscale simulations. So the gyres. The gyre is the large scale circulations in the oceans. There is main five gyres in the Earth: the North-South Pacific gyres and North-South Atlantic gyres and Indian gyres, the ocean gyres. So nowadays there's many ocean wastes are making some islands nearby the gyres because it is a circulation, big circulations. So great waste, little weight can go on to these gyres. So it is very important to get rid of waste around the ocean. Let's watch this video.
So a gyre is a natural phenomenon. A gyre is simply a rotating current system that's comprised of the Earth's rotation coupled with currents and prevailing winds. So it's essentially like a massive whirlpool, a vortex in the oceans. Say a piece of floating plastic from California in the North Pacific Gyre can take 10 years to make the rotation from California to Japan and all the way back.
So what we have found is that these plastic particles are not just in the North Pacific Gyre, they're in all 5 subtropical gyres, and all these gyres have several garbage patches in them, 8 garbage patches total in the 5 gyres.
So that was our inspiration to start the 5 Gyres Institute, to look at this plastic pollution issue on a global scale and try and show the world this is an international problem. These plastics are coming from every continent in the world, and solutions have to be on the international level. When I first heard this talk in 2001 from Captain Moore, I heard description of an island of garbage that people were calling the Great Pacific Garbage Patch. In the media, it was described as a Texas-sized island.
It's really hard to quantify how much plastic is floating in the world's oceans. These garbage patches that exist in the gyres, they're elusive, they change shape, they move around. You may trawl for 10 hours straight, you'll get a handful of plastic. You put it back in 10 hours more, and there's nothing.
So it's essentially like a plastic soup of all of this disposable waste that we create on land masses, from California to Asia, Canada, Mexico, enters this North Pacific Gyre and gets swept up into this accumulation zone.
Islands in the gyres we're discovering are the natural nets for trash at sea. It's impractical to try and scoop out trash out of the ocean. What we can do is wait for it to wash ashore. So to clean a gyre, clean your beach, clean your watershed, clean your street. As close you can get to the source is a better way we can solve the problem of plastics in the ocean.
Well, this is the end of my lecture, so thank you for listening.
Just 2 minutes. Oh, this is second part. So I try to explain about wave, reflection, reflection. Very similar, some different phenomena of wave, and then wave runoff, sediment test. Wave is a transport of energy. This comes from mainly from wind. Right? Sometimes there's a earthquake. It gives us a type of wave. Like there's different characteristics from wave coming from wind. Okay. And shallow water. So when you surfing, wave, you may notice that the faraway wave is not so high, right? But as they coming close to the beach, it can be a steep one and break down. Sometimes if you see the rough sea in video, you don't have a experience. In the big ocean, there is also wave is breaking sometimes, but that is very uncommon situation. Very high wind, then there can be. So in a big ocean, it is not easy to see the wave breaking. Always you can see the wave breaking up. At the beach, small or big, you need to have a big one for the surfing. That is because of this shallow water effect. So wave speed decrease as coming closer to the land, water depth decrease, and then finally they break. So this one shows a small picture. You may not see, but you can see that the shape of the circle is down because of the depth is skinny, right? And then finally comes become steep, and then the speed is slow, but shape is. And then you may see also the calculation equation for waves. Wave reflection. So, reflection. May change the sequence in the state, but the reflection is bounce off at the left hand side, and refraction is usually through the different medium to another. So here it shows you air is here, water is there, right? So the density is different. So the medium, we change the direction because they pass through one medium to another medium, which has different density. And diffraction involves also change of direction. This one is also change of direction, all change of direction, but different ways. So they pass through opening or around the barrier. This one is around the barrier, right? Around the barrier, so that they have a different characteristic of spreading out. The energy is spreading out. This one. So refraction was the final one. No, second one. This one. It is a little bit different one because this one comes from around the barrier. So you can see that at the top notch, you may see there are many rocks there, and there are beaches of sand and shallow water. This one can be usually rocks and steep cliffside. That's because many waves is hitting at the corner, and also the bending of directions. And also you see that from the previous lecture that water moving in this direction, each following the beach. So there are complicated water mixing up. Also, the surface water and bottom water has a different directions. So it is not simple as going on the surface. And then the wave reflection, bounce up. This one, it shows you the wave is coming and also reflected by the land, and then some videos.
Sun just set, and there's an incredible amount of physics to be learned looking at these waves and going through shallow water. What I'm looking at is I'm looking at waves traveling in towards the beach, and then waves reflecting out through the waves that are traveling in, meaning waves coming in, bouncing off the beach, and reflecting back out. Now, while they bounce back out, you can see the incoming wave interacting with the outgoing wave. What do we call it when one wave interacts with another? Let me think. Wait a second.
There's also interaction between them, right? Oncoming waves and outgoing waves are interaction between them. And diffraction is through the hole or around the barrier. But this one looks like through the hole. Energy transfer looks like this. And also there is a barrier. The wave is coming around like this. This one has two barriers up and down. So wave is coming widespread out. Spread out this way. Okay, it's transferred laterally and then through the breakwater or around the breakwater or smaller. You can see. And wave runoff is around above the still water level. This one is the still water level. So far away, ocean is in this level. Water level is here. But near the shore, wave is coming, running up to somehow, right? So otherwise, your foot can be wet. Right? If you have a running through near the shore, wave is coming and down and coming and down. So we can see that things around this point is for sure. And we can say the R can be the distance or height and runoff, depending on the size of the wave. And the sediment transport, some beach has pebbles. There are in Korea probably around the Southern Sea or South Sea. You can see the famous pebble beach with the black pebbles. Pebble Beach is a name coming from near San Francisco. There is a Pebble Beach. Have you heard of this? Anyway, so shore and near the cliff, there are different settlements of fine grain to gravels. So they are depending on the water speed and water breaking. So the sediment transportation, depending on the grain size, there's also suspensions. So if there is any suspensions, you cannot see the water clear down to the depths because of the suspension. The eye distance or looking is not good, right? So when you go to the Yellow Sea of South Korea, usually there is a mud is much mud there, so that the you cannot have a long distance views. So that is a kind of problem for fishermen, also to the Navy or submarine. But comparing to the west side of the Korean Peninsula, the east side is very clear. Depth of the water is very deep, and water is very clean because of the different suspension. And the size of the pebbles also has depending on the water and speed and streams. So sediment transportation is important, especially for coastal beaches and also along the river shore. So for the dam, you want to construct a dam along the across the river or stream. So you need to calculate how much sediment will be coming and can be deposited there. So it is usually subject of civil engineering department and coastal engineering. So resistance, so water is coming, fluid, they are pushing by fluid, but there is a friction coming from bottom and also the inertial resistance. And there are a small portion of lift, depending on the density of this object. So calculation is not simple, right? It's not, so I'm not explaining about that. There is a simple criteria, typically for the river conditions, because of the density of water, or weight is different. And then there is a rho is the density of grain. So density of grain. G may be a gravitational acceleration, and E is a diameter of this object. Right? So by using this number, you can expect it depending on the water stream speed. Okay, there is a video. It also embedded. Size 8. Trust. We also lecture material today. Question. No questions. And you can move on to the discussion session. All right. Good evening.
Let me start. My name is Wan Jin and I going to help this breakdown related to the Fokker processes. In class, we've been learning about a number of interesting waves and currents, and I'll do a quick review and move on to the discussion. First of all, transpirals are the cause of several currents, and they can represent it as the spiral pattern because it is generated by the wind, and that is caused by the Earth's rotation, and the Coriolis effect cause the flow at the surface of the ocean differ from the flow at the bottom. All of these currents affect nutrient distribution and affects marine life. Upwelling and downwelling are related to this. Usually, upwelling is caused by the wind from the north, and a downwelling is from the south. And especially upwelling also occurs at the equator. For the point where trade winds meet, the surface waters spread apart and cold water is drawn in to fill the gap. The landwear circulation is formed due to the wind stress on the ocean surface. This causing the mix of water layers, and you can see this third video is numerical simulation of the landwear circulation, and there are parallel wind to wind is to the direction of x direction, and you can see that downwelling is induced in the center and upwelling on either side of the parallel winds. I'll pass others briefly. The rip current is a narrow channel of water that flows away from the shore, and loop current is a warm ocean current in the Gulf of Mexico, and it also caused a big, huge hurricane you can see on the picture. There are 4 tweets. I hope you're volunteers. And here's one. Something estimated input for past events are entered into the model to see how well the output matches the known results. Yes. Yeah. Or, and second, upwelling or downwelling improves biological productivity. Choose one.
I think it is that one because you provide oxygen to the sea.
It could be, but in general ways, the well, provides the water into the shore. So that might be a good effect to the biological or nutrients. So it's upwelling for the general case. And third, warm ocean current that flows northward moves north into the Gulf of Mexico. Yes, it's a loop current. And the last, a set of small parallel currents that form in the ocean surface layer is related to the activity. It's related to the parallel winds. Real quick. Yeah, like landware calculation. Landware calculation. There are short discussions. This one is how might climate change affect upwelling or downwelling patterns?
Also, upwelling and downwelling can be caused by warm and cold water. For example, for the Gulf Stream in the Atlantic Ocean, the Gulf Stream is current that is upwelling near the Gulf of Mexico and goes throughout Europe, and the northern hemisphere will become a downwelling currents. But because of the ice, the melting ice, it can reduce the downwelling effect, which can stop in the end the entire Gulf Stream current melting.
That was very good point. You answered everything, so I'll go to the second question. How does the loop current influence hurricane development?
carries heat, right?
Yeah.
And the heat, wherever the loop current will go will affect the path of hurricane, since hurricane formed based on the heat.
Yeah, that is simply the correct answer. Current is warm water, so it intensifies the hurricane effects. That was correct. Questions of light first. How can we prevent the dangers of a wave current?
Even light rods on post higher position so they can see it better and warn the population.
First answer.
Have these like stuff like barriers potentially to like if it's around the area where people are, like disrupt the flow of the road.
Focus on the what's the purpose to the interrupt the waves?
Yeah, the diffraction thing we're talking about.
Yes. My question, my answer is, there are the barriers or barrier structures, such as breakwaters, and dissipate the energy of the waves, and also artificial water currents can weaken and disrupt the flow, and also the similar terms of report, deploying sensors and drones to detect and And the last question, what are the applications that we can use these currents? Use a well, yeah.
Oh, sorry, I was wondering, rip currents have something about with the water going back to sea, right?
Yeah.
Maybe you could use it to like potentially maybe optimize like you wanted to like send out like a small vessel that's like not powered really quickly, maybe you could utilize it.
Yeah. The current is very also very fast way, so we can use it for the ultimate optimize the of the vessels. Yes. Other rounder. Energy development. The upwelling or downwelling is like there are temperature differences, so we can use power generation system using that the temperature differences, and also can utilize the reed current or the loop current because it has huge amount of energy and also has a very fast waves. You can use them to generate the power, and also you can use the Langmuir circulation, because the effect of Langmuir circulation is like promote the vertical mixing, so you can supply the underwater oxygen. That's all. My last answer. Optimal efficiency operation by utilizing the direction of wind and ocean currents, considering the Ekman spiral. Yeah. That's all. Thank you for your participation.
Hope you can share your slide set, Kobe, including the answers, your answers, and then other Rose answers and your answers. All right. Any question? Any question from the online participants? How many today? No? It was earlier today also. Next time we can have more discussion. All right. What's this?